Question 6 says an equiconvex lens forms a real image of an object 3/4 the size of the object at a distance of 3 meter behind the lens. The refractive index of the lens is 1.5. The radius of each surface of the lens is, so we have to find the radius of each surface of the lens. The given information is that it's an equiconvex lens and the size of the real image is 3/4 the size of the object. The distance of the image from the lens in fact is 3 meter. So combining all this, the question of course is from the topic ray optics, and the lens maker's formula will be applied and the lens formula will also be applied. So first of all, we see that the magnification M, which is given as V by U for a lens, is in fact minus 3 by 4. Why minus sign? Because it's a real image, that's clearly given. And this means that the value of U we can find because the value of V is 3 meter. That means the value of U is minus 4 by 3 into V, and the V itself is 3 meter. So this is in fact minus 4 meter. So we have the value of U and the value of V. We can find the focal length, and applying this lens formula, 1 by F is 1 by V minus 1 by U. So that is 1 by 3 minus 1 by 4. So it is 1 by 3 plus 1 by 4. And if we simplify, well, LCM we can take as 12. And then in the numerator we have 4 plus 3, that means 7. Now we are interested in finding the radius of the surfaces. So let's bring in the lens maker's formula, which says 1 by F equals mu minus 1 into 1 by R1 minus 1 by R2. Mu minus 1 is in fact 1.5 minus 1 or 0.5 or 1 by 2. And this is then 1 by R1 minus 1 by R1 again. So it is 1 by R1 into 2. That's what we can put. R1 of course is the radius of each surface of the lens. So what we have now is that the value of R1 in fact is coming out to be as 12 upon 7 meter. And if we look at the options, it is matching with option 3. So option 3 is correct for question 6. Let's now go to the next question. Question 7 says the diameter of a sphere is measured using a vernier caliper with no zero error. It is found that the zero of the vernier scale lies between 6.20 centimeter and 6.25 centimeter of the main scale. The vernier scale has 50 division equivalent to 2.45 centimeter. The 12th division of the vernier scale exactly coincides with one of the main scale divisions. The diameter of the sphere is. So the points to note here are there is no zero error, and well, the main scale reading in fact is 6.2 centimeter. Let's find the least count, and to find the least count we see that 50 divisions of vernier are equivalent to 2.45 centimeter. So that means one vernier scale division is in fact equal to 2.45 centimeter divided by 50, which in fact is equal to, well, this will be then 0.049 centimeter. That is one vernier scale division. Now what about the main scale division? We can see that one main scale division is, because the question says the vernier lies between 6.20 centimeter and 6.25 centimeter of the main scale. That means each division of main scale is 0.05 centimeter. It's basically 6.25 minus 6.20, which in fact is 0.05 centimeter. So now that we have one MSD and one VSD, the least count we know is given as 1 MSD minus 1 VSD. As far as vernier calipers is concerned, one main scale division minus one vernier scale division, and this is 0.05 minus 0.049. If we do the subtraction, this is then coming out with 0.001 centimeter. That's the least count. Well, so the diameter of the sphere will be, in fact, the main scale reading that we have got. Main scale reading was 6.2 centimeter. So we can say the diameter is then 6.20 centimeter plus 12 times the least count. So 12 LC, and let's simplify this. This is then 6.20 plus 12 into 0.001, which means it is 0.012 centimeter. And if we do the addition, this is coming out to be 6.212 centimeter. And if we look at the options, well, we can see that it is matching with option 1. So for question 7, option 1 is correct. Let's go to the next question now. Question 8 says a pulse of light of duration 500 nanosecond is absorbed completely by a small object initially at rest. The power of the pulse is 60 milliwatt. Then find the final speed of the object if its mass is 2 into 10 to the power minus 18 kg. Take c, which is the speed of light, as 3 into 10 to the power 8 meter per second. Well, the power of the pulse is given, the duration is given, so the energy we can find, and we shall of course use the dual nature of radiation, because the radiation has both the wave nature and the particle nature. So if I consider the energy absorbed, the energy we can say is equal to power into time, and power is given as 60 milliwatt. The time is 500 nanosecond. So this energy in SI units will be 60 into 10 to the power minus 3 multiplied by 500 nanosecond. So it is 10 to the power minus 9, and the unit will be joule. Let's simplify this. We can see that this is then coming out to be 3 into 10 to the power 4 into 10 to the power minus 12. So this is 3 into 10 to the power 4 into 10 to the power minus 12, and this we can simplify again as 3 into 10 to the power minus 8 joule. That is the energy. Well, what is the momentum of all these photons? Now, to find momentum, we know that momentum of one photon is given by h by lambda, where lambda is the wavelength. So suppose n number of photons are involved, so total momentum is in fact n h by lambda of all these photons. So n h by lambda is the momentum, let's call it P. And if we look at the energy itself is n times hc by lambda. So we see that we can get E by simply multiplying P with C. So this in fact is equal to P into C, and that means we can get P, the momentum of all the photons which has been absorbed by the object, simply as E divided by C. And if we do that, this value is then coming out to be, value of E of course is 3 into 10 to the power minus 8 as we have calculated. The value of C is 3 into 10 to the power 8 meter per second, that is given, and we see that this is in fact coming out to be 10 to the power minus 16 SI units. And this we can equate to mass into velocity gained by the object. So this is mass into velocity. So the velocity or the speed of the object will be then 10 to the power minus 16 divided by its mass. The mass is in fact given as 2 into 10 to the power minus 18. This is then 100 by 2, or simply 50 meter per second. So the speed gained by the object is coming out to be 50 meter per second. And if we look at the options, we can see that option 4 is matching with what we have got. Let's now go to the next question. Question 9 says a circular loop of radius small r having 5 turns is placed with its center at x equal to root 3r on the axis of another circular wire loop of radius capital R shown in the YZ plane as shown in the figure. And small r is much smaller than capital R. The plane of the smaller loop makes an angle of 45 degrees with the x-axis. The mutual inductance between the loops is. So obviously the question is from the topic electromagnetic induction. We have to find the mutual inductance between the loops. So what we do is that we find magnetic field on the axis of the larger loop, and for finding that, let's get the formula. We know that the magnetic field on the axis of a loop is given by the formula B is equal to mu naught by 4 pi, and then current I which is flowing into 2 pi r square divided by r square plus x square to the power 3 by 2. This is the formula for magnetic field on the axis of a circular loop, where x of course is the distance of the point from the center of the loop. So now in this particular problem, the value of r is given to us. The value of x in fact has been given as root 3r. So let's substitute those values and we find that the magnetic field B in fact is coming out to be mu naught by 4 pi, and current of course I we are assuming is flowing in the loop of radius capital R. So the other term is then 2 pi r square divided by, in the denominator we have r square plus x square, and the value of x square is 3r square. So what we have in the denominator is 4r square raised to the power 3 by 2. So this is 4r square raised to the power 3 by 2. Now let's do some simplifications. This is now 2. The 2 pi gets cancelled in the numerator and denominator. The value of the magnetic field then is mu naught I, and we have of course 2 here. Now if we simplify this, r square raised to the power 3 by 2 will give us r cube, and 4 to the power 3 by 2 in fact will give us, well, 8. So this is 1 by 8 r. So this is the magnetic field due to the loop of in fact the radius capital R, and let's simplify this. This is what it is. Mu naught I by 16r is the magnetic field due to the loop of radius capital R. Now what is, let's call the larger one as 1 and the smaller one as 2. So the magnetic flux or flux of magnetic field induced in 2 due to current in 1 will be given as magnetic field due to 1, which we have already found is mu naught I divided by 16r, and this multiplied by the area of the other one and into cos 45 degree. The area of the second one is pi small r square, and because the normal makes angle 45 degree with the x-axis, this is cos 45 degree, or simply 1 by root 2. Now the importance of small r being very small compared to capital R is that we can consider the magnetic field we have derived or have got for the first loop as uniform for the small area of the second loop. So this is the expression for flux of magnetic field, and of course there are n number of turns, so 5 number of turns, we can use that too. So the total flux linked with the second one would become 5 times mu naught I pi r square divided by 16 root 2 capital R, and we can say this in fact is equal to the coefficient of mutual inductance M into I, the current in the first one, and this gives us the value of capital M as 5 mu naught pi divided by 16 root 2 r, and of course there is small r square too. So this is the value of capital M, the mutual inductance between the loops, and if we look at the options, we can see that what we have got is actually matching with option 1. So option 1 is correct for question 9. Let's now look at the 10th question. Question 10 says minimum energy required to launch a satellite of mass small m from the surface of a planet of mass capital M and radius capital R in a circular orbit and an altitude 3r. Well, the question is obviously from the topic gravitation, and in this particular case the minimum energy required will simply be equal to the final mechanical energy minus the initial mechanical energy. So let's start writing the expression for final mechanical energy as well as the initial mechanical energy. Well, the final mechanical energy, let's call it EF, would be in fact a final potential energy divided by 2, because it's in circular orbit, and when it's in circular orbit the mechanical energy would be U by 2, or that means half of the potential energy, minus capital G capital M small m divided by 8r, and initial mechanical energy EI of course is in fact would be equal to UI plus KI. We are talking about the value of UI is minus capital G capital M small m divided by R, and then there is initial kinetic energy required. So we have to equate EI to EF, and that gives us the value of KI as equal to G capital M small m divided by R into 1 minus 1 by 8, which simplifies to 7 by 8 G capital M small m divided by R. And if we look at the options, well, we can see that it is matching with option 2. Option 2 is correct. Let's now go to the next question.